Hello. I'm going to talk about the convolutional neural network prediction for the performance prediction of bismuth vanadate photoanode materials. My name is Kenji Katayama from Chuo University. Let me start from the introduction part. As you see, have been used in various fields of chemistry these days. In this context, the chemical structure of parameter X is connected with chemical properties by using the functional form Y equal f of X. For example, one of the example is drug discovery, and molecular structure is represented by X, and the activity of the drug is expressed with Y, and they are connected. And the other application is different experimental operation parameters are optimized for the action yield of Y. In the field of material informatics, in many cases, the chemical spaces, such as chemical composition, species structure, such as chemical formula, and using the DFT calculation or large database, they are connected with a target physical property or crystal structure. But in many cases, there's a problem about data number, because some of the data you can have obtained the data, but still not all varieties of the chemical targets you could have data, sufficient data. That's why these days, combined with robotic automation, so the throughput experiment has been developed, and you could increase the number of data by using the robotics automatic chemical reactions. When you think about inorganic materials applied for machine learning, let's compare. In the case of molecules, molecules can have some structural some structure by law. So you can describe these molecules easily by some sort of the rule, and using the descriptors. However, when we think about inorganic materials such as photocatalytic materials, when the light is illuminated, photoanode materials keep the water oxidation reaction. And for example, here, if it's made of the iron oxide, can you describe this Fe2O3? Because this kind of inorganic material performance is dependent also on the thickness, crystallinity, and effect and impurity. So let's know you need more information in addition to the Fe2O3. Furthermore, in the case of molecules, you can increase the number of data by using for example, DFT calculations over 1,000. However, as I said, for the case of inorganic materials, you need to have more data by preparation of the samples. So it's more difficult to increase the data in the lab scale, usually less than 100. So that's why we suppose that we can use analytical data as a sophisticated descriptors for the inorganic materials. That's our strategy. Here's our strategy we've developed. First, we prepare the device, and then analyze the performance, in this case, photocurrent for photocatalytic materials, and collection of the analytical data, various analytical data, and extracts the descriptors from the analytical data, and they are correlated with machine learning function. And finally, during the process, we can find out one of the important the analytical data for to determine the performance. So here's a strategy we published recently. And then, what we can tell is strategy works very good because the analytical methods has been selected over a long history of research. And the resulting analytical data have a potentially effective descriptors for materials. Okay, so today, many of you know in the photocatalytic P4, the PEC performance is very much important. So what if you can only take the SEM image and you can obtain the whole PEC performance, meaning the voltage current curve here, right? Isn't it great, right? So that's what we did here. So here the evaluation of photocatalytic performance and PEC performance. When the light is illuminated to the material and it's in the electrochemical cells. So what you measure is applying the voltage, and you measure photocurrent density, something like this. So in the case of photoanode materials, it's the reaction is water oxidation, which occurs at the 1.23 volt versus RAT. So you measure the current density here. So in previous research, we used the photocurrent value at 1.23 volt, which is the water oxidation potential, and then connected with this various analytical data. So, but in this case, we are going to predict the whole curve shape. So how to predict the whole curve shape? In the previous machine learning process, we used various analytical data such as XRD, Raman, UVBS, EIS, and SEM, and pick up the descriptors from the analytical data, and then they are connected with the current value. But this time we are going to use SEM images, and then they directly are connected with various for the current values, and then giving the curve. To do so, we use a convolutional neural network process. So here's the objective. We are going to predict the IV curve, a whole IV curve only from SEM images. For the bismuth vanadate, one of the famous photoanode materials, by convolutional neural network. So I'm going to explain the input data of the SEM in the next slide. So here's the SEM images we've used. We used two different SEM measurements: secondary electron image (SEI), backscattered electron image. Here I call BEI. So, and then for SEI and the BEI, we use various different magnifications of the images, like this. And also to increase the number of data which is necessary for CNN prediction, we cut the images into smaller pieces. So like m times n pixels images. Okay. So here's the CNN structure, but this one itself is kind of the very familiar, very conventional convolutional neural network structure. So we use the input data for as SEI image, BEI images, and also the overlay of two of the images, such as like RGB image in used for in a typical color image, and in any of the images, it's made of the number. So what you are doing in this structure is this is a number array, and during the convolution layer, you can detect a different pattern of the structure with different dimensions, and going down to the number information into the smaller dimensions of the number, and then they are converted into the one-dimensional number array to giving the output values, and then giving the IV curve. So photocurrent values for different voltages are predicted at the same time. And then this is a procedure for the model evaluation. So we need to evaluate how much the prediction matches with the curve, with whether we use R2 value. And if this is simply means R2 is closer to 1, it's more predictive. So what we use is the ratio of the curves is for R2 is larger than 0.95. We assume this is correctly predicted. So here's one of the example, and the dot is predicted, and the curve is measurement data. Then R2 is larger than 0.95 is in this case 31.6%. So here's the result. This is a case for SEI images, and then for the magnification of 2,000, 4,000, and 10,000 and 50,000. And the R2 ratio is 49%, 55, 56%, and 51%, and 40%. So it seems like the modification of the 4,000 and the 10,000 is giving the higher prediction ratio. Moving to the BI images, again, the match ratio from starting from 67%, the 74%, 74%, and 53%. Again, the prediction was good for 4,000 and 10,000 magnification images. You may notice that now the compare with the SCI image and the BEI images. So this is 4,000 SCI images. You maybe notice that here 55% and 51%, and using the BEI, the prediction match ratio is about 74 and 74%. So it's much better by using the BEI images to predict the curve. And also we study the effect of overlay, and here the BEI of the 4,000 and 10,000, the match ratio was 74%, but they overlaid. The case of 4,000, it didn't much change, but the 10,000 case, it's much better than the BEI. So overlay provided a higher prediction accuracy. And also, finally, we are going to optimize the cat size. Here, until now, we use a 256 by 256, but by using the Bayesian optimization, by changing the cutting size, and we optimize a match ratio to know that which size is better for the prediction. This is the result for the 4,000 magnification case. You can see simply if it's going down, the prediction ratio is much better. So it seems like going down to the smaller size better. And for the minimum point was 69 times 35 pixels. And then in the case of the 10K case, again, it's also coming down to the smaller size. There's no meaning for X and Y difference, but the 32 times 154 pixel case is better. So by using these optimized cutting size, actually, here's an amazing result that when we overlay and then the smaller size, the match ratio almost reaching 99%. And for a 10K case, you can see that it's almost like 96%. You can see almost the data points and the curve almost match very well. So almost perfect prediction is possible by using the SEM images. And finally, I will show you the line map, which it means the active area for the CNN prediction, indicated by color. Here's one of the example. It's very hard to see whether this is a case for the good prediction case. Here's an image, used image, and for different bias potentials. And it's hard to tell which is important. So we're gonna compare with a bad prediction case. And you could notice that in the case of good prediction, for different bias potentials, the similar positions were used. But in the case of bad prediction, it's randomly selected different position for different bias potentials. So similar regions used for prediction of good bias potentials. And also we studied the higher performance sample and the lower performance sample. Again, this one is very hard to see just by visually, but looking at the active region in the red region, and we could notice that so structure for prediction and performance was not by July, which was published last year in the history. So here's the take-home message. As I mentioned, that from only SEM image can you predict the PEC performance, and yes, you can. And I will show some of the demo for the calculation. Okay, so here here we have the in my computer we already have the prediction function of the bismuth vanadate for the anode. And then by using this, we can calculate the performance. So I will show this. So we have image, some of the sample image data. Let me see. So just select one of the image. So here, the raw data of the original SEM image. We're gonna use this one and hit the enter key. We cut the image, and you can use any pieces of the image. Let's select randomly here. It's too small to see, so just make it visible for you. Just hold on. Okay, it's now running. Oh, you can see. So this is a small piece. We're gonna predict the PC performance from this. So you can see some of the structure inside here, even though it's small. Okay, so Now predict using this. It takes a couple time about here, like this. So this black line is experimental data, and then red part is the predicted one. You could see R2 is very much high, like 0.9959, right? So that's totally quite very well predictable. Okay, so with that, I'm gonna finish I'm gonna finish this presentation.